Hello, everyone. My name is Kupriyanov, and this is a joint work with Daniel Tisdall. Hi, Dan. We both work at Informal Systems, and what we are going to tell you about is our work on correctness assurance for the Agoric smart contracts kernel. This project started as a security audit by Informal Systems of the Agoric smart contracts engine, and turned out into a long-term collaboration when we assure correctness of the system. In this talk, we are going first to tell you about what Agoric smart contracts are about. Then we will present different facets of how we approach correctness assurance for the system. So we have constructed a TLA plus master model. We have verified garbage collection protocol that is used in the kernel of the system. And we have done model-based testing of inter-watt communication. So where we run tests generated from a TLA plus model against the real system. So Agoric smart contracts, they're about secure decentralized finance in JavaScript. JavaScript is one of the most popular programming languages on the planet. That's why Agoric has chosen it for implementing its smart contracts. You may ask how secure is possible in JavaScript. Actually, Agoric researchers and engineers have done an amazing job in securing JavaScript. So they have turned it into a secure environment, which is based on the object capability model. An object capability is a transferable, unforgeable authorization to use some object. And all communication between different objects happens mediated and comes through the OCAP through the OCAP translation table that enforce OCAP discipline. And this prevents completely certain kinds of attacks, such as Ethereum DAO, for example. Now this system is composed of multiple layers of the stack, and it is based on the Tendermint consensus engine. And at the top of the stack, there are some smart contracts, languages, and protocols. What we are analyzing lives in the middle of this system. In particular, it is about secure ECMAScript and the object capabilities that are managed by the system. Here, JavaScript objects are administered by what's called live slots, which live in watts, which communicate via swing set kernel, and this swing set kernel manages a swing set machine. I will now tell you a bit more about different components of the system. So what is this about? Objects are just normal JavaScript objects. They're merged in this secure JavaScript environment, which is called SES. Watts are kind of processes in the system. They're unit of synchrony. Inside the watt, you can communicate synchronously, but every communication that comes outside of a watt happens asynchronously and passes through certain translation tables that enforce object capabilities. Live slots is a layer underneath the user space watt code that translates object references in the watt into something that's externally visible to the kernel. A swing set machine can contain multiple watts, and it contains a shared kernel. And this shared kernel is very much like a Unix kernel, which internally contains multiple tables for objects and promises, and again, translation tables, and a run queue of messages, how they're delivered from one watt to another watt. When a call comes from a watt to a kernel, it's called a syscall. And when it comes from a kernel to a watt, it's called a dispatch. So we analyze in our efforts specifically all of these mechanisms that how watts communicate with each other through the kernel, and how objects and promises are managed inside the kernel. Now we turn into the presentation of the master TLA plus model. And if you look at the complexity of the system that we analyze, it's pretty complex. So it's more than 10,000 lines of JavaScript and more than 5,000 lines of Markdown. What we have done, we have analyzed this system and modeled the interactions between the VATs and the kernel and how the kernel manages the objects and promises inside it. So our TLA plus kernel master model, it consists of several parts. First, we have type definitions. Then we have the master model where for each of the protocol actions, we have a type, a precondition, a postcondition, and a change and changed variables. We have the execution environment where we surround each protocol actions by certain usability improvements. And finally, we have model tests. I will just walk you through each of those components so that you can see how this works. So for type defs, we heavily use Apalache type system. In particular, it allows you to define type aliases, and for each you see you can specify what type each component of your system has. We use those type definitions in the main model file. Here, in particular, all our variables are typed, right? So you can see, for example, that the run queue has a particular type, which is defined here. It's a sequence of messages in that particular case. Then in the main model, what we have those protocol actions, and for each protocol action, we define its precondition, we define unchanged and changed variables, and we define the effect of this action. If we are talking about this action to create a VAT, the precondition says that the VAT should not be known to the system, and if it's unknown, that the update just adds this VAT to certain kernel tables. This happens for all other kinds of protocol actions. Then in the execution environment, we define certain constants. So we define how large our model can be. We define certain initializations. And finally, we surround each action with this kind of a boilerplate code, which can actually be generated automatically eventually. What we do here, we say, okay, we don't change variables that should not change. We save the action that is taken by the model, and then we check the precondition. If the precondition holds, then we execute the update. If the precondition doesn't hold, then we don't change the variables that are supposed to change and save the error. And eventually, we existentially quantify over the input variables of this particular action, and this makes this action ready to be executed in the model. And then if you look at the model, then the next predicate looks like that. So there is a certain order of actions that may happen in the kernel. So there are certain messages that may await execution. So we first execute those awaited actions. There may be a termination trigger set that will just say, okay, I just terminate this particular VAT. And otherwise, we non-deterministically execute one of the protocol actions of the kernel. Finally, we have certain unit tests for the model that just check that the model behaves in a sane way. In this particular case, we test the behavior under creating an unknown VAT or creating a known VAT. And what this allows us, it allows us in particular to trigger the type checking actions for our operators in the model. Then what we have found also very useful is type checking feature of the Apalache model checker, which was introduced recently. What you see here, you see a particular commit where I accidentally mistyped the operator name that I wanted to use. So instead of using this one, I should have used this one. What may happen if you have an ill-typed spec, that your model checking can just go fine if you use untyped specifications. What happens in the case with TLC, for example? The question is, can you trust the result of checking such specification? Luckily, Apalache now has this type checking, and it says you that, okay, sorry, your specification is ill-typed. So something doesn't match here. And what doesn't match in this case is that if you assign this operator to this index in this table, like what to kernel, it maps what IDs to certain information about them. If you use this operator, then you map a what ID to this one. So you map what ID again to what ID to what slot and to kernel slot. But as can be seen here, the type of this variable is actually that one, what to kernel, and it should be one level less, right? It should map simply what ID to what slot and to kernel slot. So there is a typo here, and Apalache type checker just catches for you this typo. Yes, now I give stage to Dan, who will tell you about verifying garbage collection protocol.
Hi, in this part of the talk, I will discuss our model of the garbage collector protocol that is in the kernel and into the VAT communication system. So we created a much more lightweight model than the master model. And it's quite an abstract model, which allows us to very practically verify some important invariants. So the swing set kernel contains a garbage collector protocol, and it's needed to ensure that objects which are exported by VATs to other VATs are eventually cleared up when other VATs no longer need them. And it involves messages between the exporting VAT, so the one that sends the item or the object to another VAT, and a set of importing VATs. And all the messages are routed via the kernel. So the VATs store tracking data to keep track of the garbage collection protocol, and so does the kernel. And so our final model was very easy to model check. I'll just give an overview of how the garbage collector works. So when an item is sent from one VAT to another, it creates several bookkeeping entries in the VATs, as well as the kernel. The exporting and importing VATs should store tracking data in their own processes, and the kernel stores its own reference in the key value store, as well as references in the translation tables for talking to the VATs. So the translation tables are needed so that each VAT can communicate with the kernel in its own language. And the protocol starts to clear up an object when an importing VAT tells the kernel that it no longer needs an object. And once all the importing VATs have done it, then the protocol should eventually free the relevant kernel data and also tell any remaining VATs who haven't cleaned up their tracking data that they can then drop the tracking data. So this diagram shows the kernel and an exporter and importer VAT. And the light bulbs showed that the VATs know about the items, they have the tracking data, and also the kernel data structures are all occupied. So there are 6 messages that are relevant to the GC protocol, 3 syscalls and 3 dispatches. A syscall is made from a VAT into the kernel, and dispatches are made from the kernel to a VAT, as Andre said. So a drop action announces that a strong reference can be downgraded to a weak reference, and the retire action announces that a strong or weak reference can be completely freed. So the garbage collector is reference counted, and the reference count should be a function of the number of syscalls and dispatches done. But that function is not always so straightforward. And so the final steps in the execution are the retire import and retire export dispatches. And that would, once those are fired, then that should signify the end of the lifetime of an object. So something we would like to know is the effect of possible malicious code. And remember that malicious code can just be the result of bugs. So even if you just have buggy code, if it allows, arbitrary code to run, then this can create an entry point for malicious code. So we want to check that a VAT who imports an item and acts maliciously cannot cause problems for the other VATs. So we want to check that a malicious VAT cannot interfere by, for example, causing the kernel to drop an object too early, or causing an incorrect message to be sent to a correct VAT. So in our model, we model 3 VATs. The model structure is quite simple. I won't show it all, but we start with an init step. And so the mode and step variables are just artifacts of the modeling. They don't have any meaning in the protocol, but they're useful for just guiding the logic of the model. You'll notice that many of the variables are Booleans. And there's also 2 integers, which are the reference counts. And because we only model 3 VATs, the reference counts are quite small. So this helps to keep the state space small. The logic of the model is shown on the right in the next operator. And we can see there's 3 different modes: try DC action, try syscall, and handle kref. So this is a dispatch step, a syscall step, and some post-processing of maybe some additional GC logic. And in our model, once we kind of inline the code, figured out what the code was doing, it was relatively easy to create the model. And then we were able to specify some invariants. So there's 2 kinds of invariants. There's one which is not so something we want to ensure happens. So we want the desired outcome of a lifetime of an object to eventually get freed once once the correct initialization of the, so once an object has been dropped, then it should eventually be completely freed from the system. So we can find such an execution by using this invariant and eventually free everything. And because we have negated this desired outcome, then when we find a violation of this, then we have an execution which satisfies the behavior we're searching for. And we could use temporal logic to express this, but using a simple invariant like this means we can also benefit from that Apalache model checker, which can also generate multiple executions which satisfy this behavior in quite a user-friendly way. Pictured on the right is the eventual state we want to reach. No VAT knows about the exported item, so that's signified with the empty light bulbs. And also the kernel data structures are clear. So this is kind of the free state at the end of the object lifetime. We can also specify some failure conditions, so things we want to avoid. So here on the left, there's an invariant exporter forgets early, which we can see we have 3 variables: exporter state, exported remotable, and importer state. And what we want to check is that no exporting VAT drops an object before an importing one, because an exported object can only be created once. So if an importer was able to access it and an exporter had dropped it already, then if an importer then referenced it in a message to the exporter, it would not be able to handle the message. So we can see that this invariant is captured in an extremely small operator. And yeah, so this was quite concise. We have more invariants. So we also want to check that the kernel never frees an object too early. So we want to check this situation. So in the right is pictured an instance of the invariant in the left being violated. So we can see that the kernel object has been freed. And the exporter still knows about the item because it has the lit light bulb. An extra kind of variable that we use here is the reachable ref count. So this is also, we want to check the case that the exporter and importer states are, even if they were correct, then we still want the ref count to be correct, because this might differ because the ref count is on the kernel logic and the state is on the VAT logic. So we need to check for any discrepancy there. We have another invariant which we check, which is we check for an unsafe free in the lookup tables, so the translation tables. And we can see here that on the right, the importer has forgotten about the object. So it's actually fine that it has no translation table entry, but the exporter still knows about the object because it has the lit light bulb, and you can see that its translation table entry has been deleted. So this is an incorrect state, which we check for with this invariant. To summarize our modeling of the garbage collector, it was a very lightweight model, and we easily checked it with TLC in a second. There was less than 1,200 states, and using this kind of very abstract model, we were able to condense a protocol which was spread over roughly 4,000 lines of code. So not to say that every line of that was relevant, but that was the kind of required amount of code needed to be comprehended. And now we have a model that's less than 200 lines of TLA plus, which gives a high degree of confidence in the protocol in the face of difficult to reason about interleavings of VAT messages and syscalls and dispatches. And one major advantage of this is now we have this spec, and it's a semantically extremely precise description of the protocol, and it's much easier and quicker to read than the documentation. So yeah.
So then I have a question here. I will take advantage of me knowing the system a bit, okay? So here you have manually constructed the abstraction, right? How would you see proving that the abstraction is actually fair compared to the system?
So I think there's always going to be space for human error, because at some point you have to make the translation from source code or documentation into a model. But you could use various techniques like refinement, for example. If you could capture the substance of the system in a very even more abstract way than this, then using refinement, you could show that this model refines that more abstract model. And hopefully by having an even more abstract model, it would be more clear that it represented the system accurately. And we could then consult an expert. So for example, the author of the system, and if they could verify that link between the very abstract model and the system, then using our refinement, we would know that this, via induction, this more concrete model indeed accurately represents the system.
Yes, I mean, this goes into the direction of even more abstraction. But what I meant is going into the direction of the code, right? That this model actually represents the code accurately.
Right, that's right. So we could go the other way. Instead of making this a refinement of a more abstract model, we could make a more concrete model which more closely resembled the code, and we would show that that model was a refinement of this model, and that model could be much richer in detail and actually model some code pathways more explicitly. So yeah, that's one way you could do that.
Okay, thanks.
So switching gears now, I'll talk about another way that we've used TLA Plus to help us check the Agoric system. So we applied a technique called model-based testing, which uses a model to generate concrete tests for a system. So we created an abstract model of a different layer, so not the garbage collector and actually not the kernel itself, but actually the user space code and the interfact communication in the user space code. So yeah, so this is great because Apalache allows you to generate thousands of executions that match specific patterns of executions in your model. So once we have generated hundreds of thousands of execution traces, we are able to convert them to concrete executions or tests using some glue code and run it directly in a JavaScript driver. So we can kind of bridge that gap from the model to actually checking the running code. So first of all, I'll just give an idea of the user space. So the Agoric system is quite powerful in the sense that user space code can contain almost arbitrary JavaScript with the additional power that two VATs can send objects to each other, and so using this OCAP system. Here are some snippets. For example, VAT A can call method foo on VAT an object sent by VAT B. With the object containing many different JavaScript types, including promises, functions, closures, and of course just data types too. So this, having so much freedom and such a powerful user space, you can do so much. It gives rise to the question of how can you write meaningful tests? So that was the challenge here. So we went about this by decomposing the possible behaviors into combinations of small building blocks. And we also modeled 2 or 3 VATs. So yeah. Instead of modeling the memory of each VAT separately, we model a shared universe that the VATs can interact with. So just a shared array of items that can be sent between the VATs and have methods called on them and so on. And you can imagine the 0 state as being the empty universe, so shown by this empty shared array. As the model execution progresses, VATs may non-deterministically add items to the universe or interact with existing items. So the VATs do not all have access to every item unless they're given access by a VAT with access, or they create the item themselves. So in this diagram, VATs A and B have created references to themselves and stored them. And you'll notice that VAT A, drawn with the dotted line, is the only VAT with access to its own reference, whereas VAT B and VAT C both have access to the reference VB. So perhaps VAT B provided access to VAT C, so it actually sent it the item. We model not only references, but also promises and their resolver functions. So in this configuration, the universe contains 2 VAT references, VA and BB, as well as 2 promises and their resolvers P0 and R0, and P1 and R1. So note that VAT A can access a resolver function for promise 1. It can access R1, even though it cannot see promise 1. So perhaps some previous steps happened and some items were sent between various VATs. And it's possible in this configuration then in the subsequent step for VAT A to resolve promise 1 using the resolver R1 to another item that it has access to. So in this case, it could resolve it to VA. And if that happened, we can see a transition here. So VAT C, which has access to P1, to the promise, once it was resolved, would then be able to see the item that it was resolved to. So in the actual system, this is these steps, exercise a lot of code, and by composing the steps in this way, we can model some quite sophisticated executions. So coming to the model and our testing system, in total we modeled 6 building block steps, and yeah, we also wrote some glue code that can take a trace, so a behavior of the model, and generate a script which can be run in a JavaScript driver, which you see a snippet of on the right. So we have 6 steps in total: send item, drop item, store a self-reference, store a promise and its resolver, and resolve a promise using a resolver to a third item. There's also like a auxiliary step, transfer control, which is we needed it in the model to know when we could switch which VAT was executing at which time. And each of these maps directly to an instruction in the JavaScript driver. And so we also have some glue code to bridge this gap, so to convert the abstract model execution into a concrete script which the JavaScript code can run, which uses like item IDs specific to the VAT. Because of course we're going from this shared universe into local per VAT memory. Yeah. So we can generate then executions, multiple executions for a behavior or a pattern that we want to see using Apalache. And you know, Apalache provides 3 components which make this really effective. So Apalache does not support generic temporal operators, but it does provide what's called a historical trace, which I'll show you shortly. That's a trace over a sequence of states. And it does allow you to generate multiple executions for a violated invariant. So you can enumerate as many as you like. And it also provides the feature to define a view operator, which is a projection that allows you to control the kind of counterexamples or traces which are generated. So for example, one pattern that we specified is using this operator. So trace resolves promise seen by other is, so this operator takes a sequence of states, which you can see with, again, with this type annotation, and it's a predicate over that. So we defined a utility operator, and then we actually specify this behavior we want to see. So this behavior is looking for 2 indexes in the sequence of states, so the history, in which state I, or the transition from state I to I+1 is a promise resolution step. And state J, which succeeds I, does not have the same acting VAT as state step I. So that can be seen in where it says acting VAT is different in states I+1 and J. And then there's a check to check that we that step made by in step J is not just a auxiliary step. So we want actually a meaningful step there. So many of the behaviors we generate here, well, all of them will include a promise resolution, and many of them will include a, not only is the promise resolved, but also a different VAT is able to then use the resolved promise for a subsequent step. So it's quite an interesting behavior, which we can specify like this and generate thousands of counterexamples for. Apalache also provides a view. So it's a function of the state, which Apalache says it uses to determine if it should consider 2 states to be different when it generates counterexamples. So here, one we used was exploratory view, and so it's a function of the step count and step variables, which are the kind of actions chosen. And so what this is saying is Apalache will say states A and B are different if the step variable is different, and one of the steps has a step count of 4 or more. So what this allows is, because Apalache will only generate counterexamples which are different according to this, then we ensure that each counterexample uses a different sequence of steps in the suffix of this step sequence. Whereas the prefix might actually, it can be the same because you won't be able to differentiate in that case. So this means that.
Then I have a question here. You have used both Apalache and TLC for generating multiple counterexamples, right?
Right.
How would you compare like the abilities in that respect?
So I would say Apalache is much more feature rich in that respect. While TLC, it provides a continue parameter. So it allows you to essentially say that you want to continue model checking when an invariant is violated, but you have very little control over how that happens. So you're kind of at the mercy of the like the BFS algorithm essentially, and you may generate many counterexamples which are not meaningful because you don't have this view. So TLC does give a view feature, but it actually has different semantics from this, so it's not relevant in this case. Also, TLC has the added issue that you could accidentally cause the model to run forever, whereas Apalache is a bounded model checker and will check like the diameter per diameter of your execution. So for this model-based testing, Apalache is crucial right now.
Okay, thanks.
So to summarize, I'll just kind of describe the effort to reward ratio of this MBT approach. So we needed 200 lines of JavaScript code to actually run the script, around 300 lines of glue code to translate executions into a script for the JavaScript. And we needed about 200 lines of TLA plus for the model. Once we have defined like an operator to match a pattern of behavior, depending on the complexity of it, we were able to generate one trace from every second to a few seconds up to like a couple of minutes. So using this approach, you can generate thousands of tests for a given behavior. The behaviors can be as simple or as complex as you wish, depending kind of on how long you want to wait, essentially. And the real advantage is you can generate tests for a complex runtime environment using a very abstract model, and it's kind of depends on just the nature of the model and how much gluing you want to do just to generate any auxiliary parameters that are needed in the real runtime. And this is really useful because the test can be easily incorporated into a CI or regression suite. You can just accumulate many tests for many different things, and just explore a huge number of pathways in the code with relatively little effort. So yeah. So thank you very much for listening, and maybe Andre would like to say something too.
Yes, thank you for listening to our talk. Please check out, here are some references for you to check. And in general, we are very much happy to be involved in projects around correctness assurance, and in particular with TLA+. Yeah, thank you.